Hello all, welcome to today's session on orthogonal projections. In yesterday's sessions, we saw what do we mean by projection, what are the two basic types of projection. Projections are classified into two types, parallel projection and perspective projection, right? So parallel projection is a projection wherein which we are drawing parallel lines from the vertices of the object onto the view plane, right? So and we can see the complete view of the object which is projected on the view plane, right? So the relative proportions of the object will be preserved if I take the parallel projection. Whereas in perspective projection, right, so the projection lines are drawn from all the vertices of the object and they will converge to a point which is called as the projection reference point, right? So when I'm taking perspective projection, right, so the relative proportion of the object is not preserved, right? So the object will be reduced in size. So we can say that it provides a realistic view. The perspective projection provides a realistic view, whereas the parallel projection does not provide a realistic view. So under the parallel projection, we have orthogonal projection and oblique projection as the two types, right? So today we'll be seeing a little bit in detail about the orthogonal projection. So a transformation of the object description to a view plane along the lines that are parallel to the view plane normal vector, right? So that means if I take the projection lines which are parallel to the normal vector, that means if I take, then three normal vectors are x-axis, y-axis and z-axis. If I take my projection lines which are parallel to x-axis, or if I take my projection lines which are parallel to y-axis, or if I take my projection lines which are parallel to z-axis, right? So then I can view that particular type of projection as orthogonal projection, and I can view that particular projection as orthogonal projection, and it is also called as orthographic projection, right? Or in short, we can say that if I have any projection transformation where the projection lines are perpendicular to the view plane, right? So if the projection lines are perpendicular to the view plane, then also it is called as orthogonal projection. Orthogonal projection are basically used in order to produce the front view, the top view and the side views of the object. If I consider this as my object, if I want to see the front view of the object, right, then I can draw the projection lines from each of the vertices of the object such that they are perpendicular to the view plane, or I can say parallel to z-axis, right? So I can see the front elevation view. If I have to see the side view of the object, then what I do, I will draw the projection lines from each of the vertices of the object onto the view plane such that they are parallel to x-axis, or I can say they are perpendicular to the view plane, right? So what view I will get is the side view. Then coming to the third view, which is called as the top view, right? So or the plane view. If I have to see the top view of an object, then what I can do is I can draw lines from each of the vertices of the object, right? So which are parallel to y-axis, right? So or I can say which are perpendicular to my view plane above, right? So top view plane. So this is the front view plane, this is the side view plane, and this is the top view plane, right? So front side and rear orthogonal projections of an object, we call them as elevations, and the top orthogonal projection is called as a plan view, right? So the front view, the side view and the rear view, right, so of an orthogonal projection we call them as elevations, whereas the top view of an orthogonal projection is called as the plan view, right? So the next topic is axonometric and isometric orthogonal projections, right? So we can also form orthogonal projection such that it can display more than one face of an object, right? So if I take this particular orthogonal projection, either I'm having the front face of the object, or I'm having the side face of the object, or I'm having the top face of the object. But if at all I want to keep my object tilt, right? So look at this cube, I have kept my cube tilt and I want to see more than one face of an object, right? So that is also possible. Such type of views we call them as axonometric orthogonal projection, right? So an orthogonal projection where I can see more than or which displays more than one face of an object is called as axonometric orthogonal projection. So the most commonly used axonometric projection is the isometric projection, right? So isometric projections you have already done in your CAD subject, right? So where we will have the projection where I can see more than one face of an object, right? So it is generally obtained by aligning the projection plane so that the plane intersects each coordinate axis in which the object is defined, right? So that means it should intersect the x-axis, y-axis and z-axis, right? So now they are called as the principal axis, right? So we can see here I have the x-axis, y-axis and z-axis. These three axes are called as principal axis and are at the same distance from the origin. Now coming to the orthogonal projection coordinates, right? So if at all I take this example where I have my point, the point is x comma y comma z, it is projected onto a view plane, right? So it is projected onto a view plane in the direction which is parallel to my z view axis, right? So if at all I project any point which is parallel to the z view axis, right? So then the coordinates of that particular point on the view plane will be xp will be equal to x and yp will be equal to y, right? Because z is equal to z view axis, right? So z is equal to z view axis, therefore xp and yp will be equal, xp is equal to x and yp is equal to y, right? So these are the orthogonal projection coordinates, right? So let us move on to clipping window and orthogonal projection view volume, right? So we have already seen the concept of 2D clipping, right? So what is clipping? Clipping is nothing but selecting that particular part of the object which we want to display on the display screen, right? So in an OpenGL, we basically we set up a clipping window for 3D viewing, just as we did for 2D viewing. And we know that the coordinates of a clipping window are xw min, yw min, that is the leftmost corner of my clipping window, and the rightmost corner of the clipping window is xw max and yw max, right? For 3D viewing, the clipping window is positioned on the view plane, right? So for 3-dimensional viewing, what we do on the view plane, I will position my clipping window with its edges which are parallel to the x view axis and y view axis as shown in the figure below, right? So my edges, you can see the lower edge is parallel to my x view axis, right? And the height of the clipping window, it is parallel to the y view axis. If you want to use some other shape of the orientation also, we must develop our own viewing procedure, right? I can also place this particular view plane or the clipping window in whatever axis I want, right? So in this example, we are taking in such a way that my lowermost bottom of the clipping window is parallel to x view axis and height is parallel to my y view axis, right? So the edges of the clipping window, they specify the x and y limits for the part of the scene that we want to display. The edges of the clipping window, they specify the x limit and they specify the y limit, because here x is varying from xw min to xw max and y is varying from yw min to yw max, right? So these limits, they are basically used to form the top and bottom and the two sides of the clipping region, right? So it is also called as, this part is also called as the orthogonal projection view volume, right? So if I take any projection lines, right, because which are perpendicular to this view plane, right? So if I take the projection lines which are coming, right, and which are falling onto the clipping window, right? So we can see that these projection lines form the four boundaries of the plane, right? So and they are also perpendicular to the view plane and they pass through the edges of the clipping window to form an infinite clipping region, right? The projection lines are perpendicular to the view plane, right? So if I take any projection line which is drawn from the object, right, so that has to be displayed onto this clipping window, we can see that the projection lines are perpendicular, because I'm considering the orthogonal projection. Since the projection lines are perpendicular to the view plane, the four boundaries are also planes, right? The four boundaries of the clipping window, they are also planes which are perpendicular to the view plane, right? And they pass through the edges of the clipping window to form an infinite clipping region, right? So if I look from the side view, I will get a view like this. If at all I look from the top view, right, so this is my clipping window, right? So I'm looking from the top, right? So this is how the clipping window forms a clipping region, right? So these two planes are called as this is called as the near and the far clipping plane, and this is called as the front and the back clipping plane, right? So the near and the far planes, they allow us to exclude objects that are in front or behind the part of the scene, right? So near and far means they will not allow us to see the objects, right, which are in the front or behind the scene, right? So only if I take the near plane, I cannot see the view of the object which is far, right? So if I take the far plane, I cannot see the view object which is in the front, right? So when the near and the far planes are specified, we can obtain a finite orthogonal view volume, right? So when I have a near plane and when I have a far plane, right? So the orthogonal projection, I can obtain a orthogonal view volume. This orthogonal view volume, we call it as a rectangular parallel pipe, right? So as shown in the figure below, right? So this is my clipping window. I'm considering the four axes which are perpendicular to my view plane, right? So when I join these four axes which are perpendicular to the view plane, right? So this clipping window, it forms a view volume with the near plane and with the far plane, right? So this is how it looks like. So the next topic is normalization transformation for an orthogonal projection, right? So as we have normalized our 2D viewing, right? So where our clipping window is normalized to a square, the same way I can also have normalization transformation for 3D viewing, right? So you have to refer page number 234 in the textbook, right? So that you will be able to clearly understand how we are using this projection matrix, right? So once we have established the limits for the view volume, the coordinate descriptions inside this rectangular parallel pipe are the projection coordinates, and they can be mapped into a normalized view volume. That means we can normalize this orthogonal projection view volume by applying the transformation, right? So in order to normalize, always we will consider a unit cube, right? So unit cube with each x, y, and z coordinates in the range from 0 to 1, right? So this normalization transformation approach is to use a symmetric cube with the coordinates in the range from -1 to 1, right? So you can see here in our 2D screen, we had the same diagram we had where we were displaying a red triangle, right? So here I can display a pyramid, right? So in the 2D viewing or 2D clipping, right? So I had only x and y screen, right? So but here now I have x screen, y screen, and z screen also, and I can see the 3D view of the object, right? So we can convert the projection coordinates into positions within the left-handed normalized coordinate reference form, and these coordinate position will then be transformed to the screen coordinates by the viewport transformation, right? So that means first we have to normalize such that they will be converted into screen coordinates, right? So once we get the screen coordinates, then finally we have to convert them to the viewport coordinates, right? So to do that, what we do is we have the orthogonal projection view volume, right? So here we have xw min, yw min, z near. As we saw that whenever I have the view volume, I'll have two types of planes. One is near plane, the other is the far plane, right? So the same rectangular or parallel pipe I am considering here view volume, right? So xw min, yw min, z near. Here I will have the topmost end as xw max, yw max, and z far, right? So now this particular orthogonal projection view volume should be normalized, right? So when I normalized it, right, in the range from minus x, minus y, minus z to positive x, positive y, positive z, right? So since it is a unit cube, I will take it as -1, -1, -1 to 1, 1, 1, right? So this is my x normalization, y normal, and z normal. So the normalization transformation for the orthogonal view volume, right? So orthogonal view volume is normalized, right? So this is the same transformation matrix what we have seen in case of window to normalized square, right? So you can refer page number 234, right? So there we have a projection matrix for window to normalized square, right? So the same thing we have written just by including the z coordinate, right? So there we had 2 divided by z, xw max minus xw min, 0, 0, minus xw max plus xw min divided by xw max minus xw min, right? So again 0, 2 divided by yw max minus yw min, 0, minus yw max plus yw min divided by yw max minus yw min. Again 0, 0, right? So minus 2 divided by z near minus z far, right? So we are considering this for z axis. 0, 0 followed by, because on z axis x and y coordinate will not be there, right? So for z value, I am taking it as minus 2 divided by z near minus z far, and this is z near plus z far divided by z near minus z far, and this is 0, 0, 1, right? So this is our homogeneous matrix representation in order to normalize the orthogonal projection view volume, right? So let's move on to the next topic, which is called as perspective projection, right? So what is perspective projection? A perspective projection is obtained whenever I have my projection lines converging to a position which is called as the projection reference point, right? So this projection reference point, I call it as the center of projection, right? So the objects are then displayed by the foreshortening effects, and projection of distant objects are smaller than the projection of the objects of the same size that are closer to the view. That means I can there is a difference between perspective of projection of an object which is very close to the view plane and the perspective projection of an object which is far from the view plane. The more far the object is, right, so we will get the smaller view of an object on the view plane, right? I can see that particular object is very small size, right? So if I take that object as very close to the view plane, then I can see comparatively larger size of the object will be displayed on the view plane, right? So this is with respect to perspective projection. The far the object is, the smaller the size will be displayed on the view plane. The near the object is to the view plane, I can see a relatively larger size on the view plane, right? So next, let us see how we can have perspective projection transformation coordinates, right? So how we can define coordinates for perspective projection. This figure shows that a projectional path of xyz, right? So I have a point P which is x comma y comma z, right? So this is displayed on a view plane, right? So on a view plane by using the perspective projection, right? So when it is displayed on the view plane, right, so it is displayed parallel to z axis, right? So it has displayed parallel to z axis and it is displayed on the view plane. Then now, what is the projection reference point? The projection reference point is some point which is far from the view plane, right? It is somewhere here. It is after the view plane. I will have a point. That point will be incident on the view plane, and all the lines of that particular object, they converge at one point, right? So always projection reference point will be at a very far distance, right? So this projection reference point coordinates are XPRP. XPRP stands for X projection reference point, Y projection reference point, and Z projection reference point. As you can see here, the projection reference coordinates are X projection reference point, Y projection reference point, and Z projection reference point. This P is equal to x comma y comma z is my original point which is projected onto the view plane, right? So now the projection line, it intersects the view plane at a coordinate position, right? So it is intersecting on what? It is intersecting and it will form the point as xp yp comma zvp, right? So zvp is selected, it is a selected position for the view plane on the z view axis, right? So because it is displayed on the view plane, right? So we have the x and y axis, right? And this particular line, it is parallel to my z axis. Since it is parallel to z axis, I will take my coordinate as a z view p, right? So on the z view axis. And we have few equations which are written. We can write the equations for the perspective projection in parametric form, right? So we write x dash. X dash is nothing but the new point which is formed on my view plane. X dash is equal to x minus of x minus xprp into u, right? So y dash is equal to y minus of y minus prp into u. Z dash is equal to z minus of z minus zprp into u, for 0 is less than or equal to u is less than or equal to 1. These are called as the parametric equations which are written for perspective projection. These are written, right, basically by considering the symmetric triangles, right? So these are the standard equation. So on the view plane, what we have, we know that what is z dash? Z dash is equal to zvp, right? So x dash is xp, y dash is yp, and z dash is zvp. So on the view plane, we have z dash is equal to zvp, and we can solve for the equation for z dash, right? Z dash equation for parameter u, right? So what we will get, u will be equal to, just replace z dash by zvp, right? So I will get it as, right, so zvp plus zvp minus z, sorry, z minus zvp, zvp minus z will be equal to, zvp minus z will be equal to, you have to multiply this, right? So you will get it as a minus u into z minus z prp, right? So just take this u, you have to calculate u. So u will be equal to what? U will be equal to zvp minus z divided by zprp minus z, right? So if I consider this equation, z dash is equal to z minus of z minus zprp into u, right? So just substitute for z dash as zvp and transform this equation such a way that you will find out the value for u, right? So if I transform, I will get it as u will be equal to zvp minus z divided by zprp minus z. This is the value for your u value, right? So parameter u. Now I have to substitute this u value into my equation for x dash and y dash, right? So what is x dash? X dash, we know that it is a new point on the view plane, which is xp. And what is y dash? Y dash is the new point on my view plane, which is yp, right? So I will write here, I will get it as xp is equal to x, right? Xp is equal to x minus, what is u value? U value is zvp minus z divided by zprp minus z, right? So I will get here as x into u, right? So whatever is the value of the u, I am writing that minus into minus, I will get it as a plus, right? So xprp into, I have to replace the value of u, right? So here what we are doing for xp is nothing but the difference between x dash and x, right? So x dash minus x, sorry, x minus x dash, x minus x dash is my xp, right? Y minus y dash is yp, right? So what we'll do is x minus x dash, I will write it as xp, and y minus y dash, I will write it as yp, right? So then I will get, so if I take x minus x dash, what will be remaining here? I will get it as ux, right? So plus au into xprp, right? So just multiply that, you will get the answer, right? So just substituting the value of u, you will get it as x into zprp minus zvp divided by zprp minus z plus xprp into zvp minus z divided by zprp minus z, right? So here for yp, you will get it as a y into zprp minus zvp divided by zprp minus z plus yprp into zvp minus z divided by zprp minus z. You just have to substitute the value of u into these equations, right, for x dash and y dash, right, and we will obtain the general perspective transformation equation. Now you have to consider this equation as the basis. That this is very, very important. These equations are the basis for all your perspective projection equation cases. Right, so we have 4 special case. What is the first case? Case 1 is, in order to simplify the perspective calculation, what we do, the projection reference point could be limited to position along the z view axis, right? So that means I am taking the projection reference point on z axis, right? So if I take my projection reference point to be along the z view axis, that means on the z axis x is 0 and y is 0, right? Therefore my xprp will be 0 and yprp will be 0. So substitute xprp as 0. Uh, this entire uh, this entire part of the equation will get cancelled. I will get only x into zprp minus zvp divided by zprp minus z, right? So yp, again yprp is 0, so 0 into this will be 0, so I'll get yp is equal to y into zprp minus zvp divided by zprp minus z, right? So this is the first case of parametric projection equation, right? So where we are considering that the projection reference point is along the z view axis, right? So if I take along the z view axis, I will have my x projection and y projection reference points is to be equal to 0. Case 2, sometimes the projection reference point is fixed at the coordinate origin, right? So if at all my projection reference point is at the origin, so at the origin we know that it is x is 0, y is 0 and z is 0, right? So therefore xprp, yprp and zprp will be 0, right? So substitute the values of xprp, yprp and zprp as 0 in this equation, right? So if you substitute 0 in this equation, right, so you will get it as xp will be equal to x into, right, zvp by z, x into zvp by z, and yp will be equal to y into zvp by z, because your zprp is 0, right? So 0 minus zvp, 0 minus z, you will get it as minus zvp minus z, right? So minus minus will get cancelled, you will get it as zvp by z. xprp is 0, so this entire term will go. Yprp is 0, so this entire term will go, right? So you just have to substitute 0 0 0 for xprp, yprp and zprp. You will get the values for xp and yp. Now case 3, in this case 3, right, so if the view plane is the UV plane, right? So if at all the view plane is considered to be as one more plane which is UV plane, and there are no restrictions on the placement of the position reference point, right? So this projection, what we did is in such a way that I have having a view plane, and this particular view plane, it is parallel, and the point whatever I am projection, and the projection whatever I'm doing is I am taking as parallel to z axis, right? So I'm doing parallel to z axis. That is why I say that a position on the view plane on the z view axis, right? But if at all I take any projection such that it is some other plane, it is some other plane, right, which is UV plane, and there are no restrictions on the placement of the position reference point, then I will have to take this ZVP value as 0, right? So if I substitute this ZVP as 0, right, so in this equation ZVP as 0, what I will get, x into ZPRP divided by ZPRP minus Z plus XPRP into this is 0, so I'll get it as minus Z divided by ZPRP minus Z, right? So like this, we substitute the values and I will get the new values for XP and YP. Just substitute ZVP as 0 because I'm considering one more view plane, right? So it is the UV plane and there are no restrictions on the placement, right? So yeah, the previous equation we considered such that we are placing the view plane in the Z view axis. So if at all we are not considering the Z view axis, then it will be ZVP will be equal to 0. So next we have the last case, case 4, which is with the UV plane, right? So as the view plane and the projection reference point on the Z view axis, right? So if at all I take UV plane as the view plane, right? So here I am taking UV plane as the view plane and there are no restrictions on the placement of projection reference point. If at all I am taking UV plane as the view plane and the projection reference point on the Z view axis, right? So at that time I will have XPRP equal to YPRP is equal to ZVP as 0, right? So substitute these values, right? So in your base equation, that is this equation, substitute XPRP, YPRP as 0 and ZVP as 0, right? So you will get the new values for your XP and YP. So XP will be equal to X into ZPRP divided by ZPRP minus Z, and YP will be equal to Y into ZPRP divided by ZPRP minus Z. Just substitute these values as 0 in the previous equation, right? So the view plane is actually placed between the projection reference point and the scene, right? So we will have an object and we will have the view plane here, right? So all the lines from that particular object will be converging to form a reference point, so which is away from the view plane. That means I say that the view plane is actually in between the projection reference point and the scene, right? So but in general the view plane could be placed anywhere except at the projection point, right? So you can place the view plane anywhere. So if at all I place my view plane which is behind my projection reference point, right? So at that time what will happen, I can see that the object view is inverted, right? So if at all the projection reference point is in between the view plane and the scene, right? So if this is the scene, I want to display a line which is upward, right? But my projection reference point has a center of projection is in the center and the view plane is at the last, then what happens, I will get an inverted image. I will get an inverted image of the scene on the view plane, right? So perspective effects, they also depend on the distance between the projection reference point and the view plane, right? So if I have a projection reference point, right, and my clipping window, right, so the distance is very lesser, then I can see the object at a bigger size, right? So if at all my projection reference point is very far, right, so then my object size is also reduced, right? So if at all I have very far from the view plane, right? So like this I can have different, the perspective effects, they depend on the distance between the projection reference point and also the view plane, right? So if the projection reference point is very close to the view plane, perspective projections are emphasized. That is, closer objects will appear much larger than more distant objects of the same size, right? So if the object is very closer, right, so then the object will appear much larger. Similarly, as the projection reference point moves farther from the view plane, right, so then the difference in the size of the near and far object decreases, right? So if it is very far, right, then what will happen, then the size or the difference will decrease, right? Difference between the size of the near and the far object will decrease, right? So the next topic what we are discussing is vanishing point, right? So vanishing point is nothing but the your convergence, your center of projection reference point, right? So which is the convergence point, right? So where all the projected parallel lines meet or converge, that is called as the vanishing point. The point at which it is same as your center of projection, that is your projection reference point, XPRP, YPRP and ZPRP. That is only called as the vanishing point. So the point at which all the projected parallel lines they appear to converge is called as the vanishing point, right? So each set of projected parallel lines have a separate vanishing point. That means if I project here, I will have one vanishing point. If I project this side, I will have one more vanishing point, like that, right? So each set of projected parallel lines, they have a separate vanishing point, right? So for a set of lines that are parallel to one of the principal axis of an object, right? So this line, it is a parallel to Z axis, right? So the vanishing point is referred to as the principal vanishing point. So we can control the number of principal vanishing points. That means we can have one vanishing point, we can have two vanishing points, or we can have three vanishing points with the orientation of the projection plane, right? Because we have three axes, so we can have maximum three vanishing points, right? So that is why we say the perspective projections are classified into three types, right? So as I have told in the last video also, the perspective projections are classified into three types, which are 1 point perspective, 2 point perspective and 3 point perspective. So principal vanishing points for perspective projection views of a cube, right? So this is the cube. What are the three principal axes of a cube? I have x-axis, y-axis and z-axis. So when the cube is projected to a view plane that intersects only the z-axis, right? So if at all the cube is projected such that it intersects the z-axis, then I will get a single vanishing point on z-axis, right? So this is called as 1 point perspective projection. So what if the cube is projected to a view plane such that it intersects both the z-axis and also the x-axis, right? So if at all I'm considering the view of an object, right? So this is the cube of the object. If at all I will project in such a way that I'll have in such a way that that particular view plane intersects both the z-axis and x-axis, then I will get two vanishing points, right? So one vanishing point on x-axis, one vanishing point on z-axis, right? So the same way I can have 3 point perspective also, right? So to draw 3 point perspective, I can take an example of a triangle. As I have told, if you consider a triangle like this, right? So then at the bottom side of a triangle, if you are projecting, you will get one vanishing point, right? At one side of the triangle, you will get one more vanishing point. At this side of the triangle, you will get one more vanishing point. That means for a triangle, how many vanishing points are there? There are 3 vanishing points. So a perspective projection view volume, it is often referred to as the pyramid of vision because it approximates the cone of the vision of our eyes or a camera. Yes or no? Right? So because we are seeing from our eye, an object, whatever we want to see, we are seeing from our eye, right? So if at all this is an eye and I want to see this object, right? So it forms a cone of vision, right? So this looks like a cone. So we say the cone of vision is formed, right? So this particular cone of vision, right? So it includes only those objects within the pyramid, right? So whenever I see from the far, right? So what happens? A pyramid is constructed, right? So the objects which fall within this particular cone of vision, right? So or the pyramid, right? So is can be seen, and those objects which are outside the cone of vision we cannot see, right? So and by adding the near clipping plane and the far clipping plane, right? So which are perpendicular to the z view axis, right? So we chop off the parts of the infinite perspective projection view volume to a truncated pyramid, right? So that means we will cut off all the far infinite views, right? Infinite parts, right? And we can see whatever is there between the near and the far clipping plane, right? So this truncated pyramid, we call it as a frustum or the view volume, right? So this is our rectangular frustum or view volume, right, of our perspective projection, right? So this we have already seen in our 4th lab program where we were discussing about the perspective projection. This is our truncated pyramid, which is called as the frustum. It has a 2 clipping planes, near clipping plane. The plane which is near to the clipping window, I call it as the near clipping plane. The plane which is far from the clipping window, we call it as the far clipping plane, right? So but with the perspective projection, we could also use the near clipping plane to take out the large objects because it is very close to the viewing plane, right? So on the near clipping plane I can have the large objects, whereas on the far clipping plane I can have the small objects to be displayed, right? So in the next session, let us take on about what do we mean by perspective projection transformation matrix. So far we have discussed about what is orthogonal projection, right? So what are the different views of orthogonal projection? Top view, side view, right? And front view, right? So we can also have different views of an orthogonal projection by making use of the axonometric projection, right? So if I want to see different face of an object, right, so I can do that. We can also go for normalization of the orthogonal projection, right? So for normalization, we are doing the same thing as how we normalize window to viewport, right? So you can see my video on window to viewport where we are normalizing, the transform. We are having the normalization transformation matrix. So same thing is written, only the z component is added here, right? So next we saw perspective projection, how far objects will be displayed bigger, right? Sorry, near objects will be displayed bigger compared to far objects, right? So what are the projection coordinates, how to calculate them, what are the different cases we have to consider in order to find out the perspective projection coordinates, right? And what are the three types of perspective projection, right? Based on the vanishing point, the perspective projection is classified into three types, right? 1-point perspective, 2-point perspective, and 3-point perspective, right? And we say that since the perspective projection, right, so it forms the cone of a vision, right? So this cone of a vision produces a truncated rectangular pyramid, which is called as the frustum, right? So this is called as the view volume. So this frustum has two planes, near clipping plane and far clipping plane. The clipping plane which is near to the clipping window is the near one, right? So which is far from the clipping window is the far, right? So the larger objects can be displayed on the near clipping plane and the small objects can be displayed on the far clipping plane, right? So in tomorrow's session, let us discuss about how to obtain a transformation matrix for perspective projection. Thank you.